Video on the channel. In today's video I'm going to be explaining how to use Lenz's law and what Lenz's law actually is. So if you have any questions at all during the video, leave something in the comments and I'll try my best to answer it. But this is pretty much what it is in a sense here. So we have a magnet with a north and a south pole, so that's what a magnet is. And all you're doing is you're moving it through a closed wire pretty much, okay? And all you've got to do is work out which direction the current would be flowing in. Whether it be going this way or would it be going that way, okay? So there's some things we've got to understand, okay? So an important concept is what flux is, okay? So flux, if we were to think about it, might have this symbol here. Magnetic flux specifically is the amount of magnetic field going through a certain area. So for example, let's say we have an area like this, and let's say these are magnetic field lines. This would not have a lot of flux because while there is a big area here, there isn't a very strong magnetic field strength. The formula for flux would be something like this. So that's magnetic field strength times area. This would have a lot of flux if the magnetic field strength was very strong. However, if you had a small area but you had a very strong magnetic flux or something like that, a very strong magnetic field strength and a small area, you would have low flux, okay? So flux is proportional to both magnetic field strength and the area in which it's going in. Why that's important for Lenz's law is the fact that it will be increasing and decreasing. So here, if we were to draw our field lines in, so the way I remember field lines is they always go north to south on the outside, so something like this here, okay? Now, the direction we want to pay attention to is specifically this direction here inside the field, okay? So if I'm moving this magnet towards the coil, what we've got to understand is the flux increasing or decreasing. So what that means is, alright, is the amount of magnetic field strength going through the area increasing or decreasing? Is there more or less at certain moments in time? So as this magnet moves towards it, we can see there is more magnetic flux because there is more red lines going through that field there. Once it hits the middle though, what we're going to start to see very shortly is once it starts going through that center bit there, it's going to start to decrease because once it's moved through it, it'll be here and then it's going to start decreasing. So it's all about a moment in time here, okay? Now Lenz's law basically says an induced current produces a magnetic field that opposes the change in flux. So here, let's say I'm moving this towards here. What we've got to understand is, alright, is the flux increasing or decreasing? Because it's going towards it, the flux is increasing, okay? So we need to create an induced current, an induced magnetic field that opposes that change. aka it opposes the direction of this arrow here. So what that means is our induced magnetic field will be in the opposite direction to that arrow. So it will be this way because if the flux is increasing, we want R1 here to decrease it, which means it would oppose that direction there, okay? Then you want to use your right hand rule. So your right hand rule basically says that your thumb is the direction of, the magnetic field, and the fingers are your currents pretty much. So if I were to point my right thumb in the direction of this and curl my fingers around, the current is going to be going around like this. And that's all it is. Okay? So the current in this case here would be going anti-clockwise. Okay? So if you want a specific definition, I can write it here, if it allows me. So let's go Lenz's law. The induced current produces a magnetic field. We'll go through the loop. Oh, it's over there. That opposes the change in flux. Now notice it's the change in flux, not actual flux itself. The change in flux, okay? Let's do another example. Let's say it was the other way, or let's say it was sideways pretty much. So if I were to move, I can leave this example up here, but it's not really going to help us too much. It's more so this idea here. So if we had, let's say, another magnet let's say it's let's go north up here and south here, and let's say we are moving it through this one here. So a loop like this. That's a terrible little loop. Let's turn on link to shape. See if that makes something a bit better. Yeah, that can work. Okay. So let's say we're moving it towards here. Now, first of all, you got to draw in your field lines first. So remember, it always goes north to south on the outside. So the direction we want to pay attention to is that inside bit. So realistically, we're only looking at this guy here. Now, let's say I'm moving this away. Okay. What we want to understand is the flux increasing or decreasing? Well, think of it like this. These field lines are like this. They go all the way out there. If I'm moving the magnet away, what's actually happening is there are less field lines going through that area at a specific moment in time. So here, the flux is decreasing. So what that means is our induced magnetic field wants it to increase. Okay? Now, to increase, you have to go with the direction. So notice the line is facing this way. That means our induced field will have to go in the same direction. So it'll be going this way here. Then again, you're using the right-hand rule. So stick your thumb in the direction of the orange arrow and curl your fingers around. And again, we get this direction here. So it's anti-clockwise again for this situation here. Now, don't base it off the north and south. Always just check, is the flux increasing or decreasing? And then it's whether you're opposing that change, okay? So if you're trying to make it increase, you go with it. If you're trying to make it decrease, you go against it. Let's try one of these questions here with a solenoid. So we'll go with one of these guys here. Just getting off a different page, sorry guys. Hopefully that stays there. Let's get rid of this. And I'll get rid of this. So we have something like this here. Oh, that got rid of our definition very quickly. Okay, so let's say we had something like this. We want to work out the direction for this situation here. Now, whenever you have a sideways example, I always like to draw it vertically. So I'm looking at the line, the wire closest to the magnet, which would be this guy here, and I'm making a circle about that. Now, ideally, I want to try and make it like that. So this bit here matches that bit there. Now here you've got let's draw a magnet, north and south. So your field lines go north to south. So something like this. And the direction we're paying attention to is this bit here. So first of all, because they're moving it away, we will understand, is the flux increasing or decreasing? Now, because it's going away from the loop, the flux is decreasing, which means our induced field wants it to increase. So we want to put a line that goes the same direction as this guy here. So we want it facing down in this case here. Then you're going to stick your right thumb in the same direction, curl your fingers around. So this time it's going this way here. Now this is the tricky bit. We need to now map this onto the solenoid. So that blue bit, if I were to turn it to, if I were to like rotate it 90 degrees, I would have it going, quote unquote, this way here. Once I know it's going that way, I know that's going this way for the rest of these guys here, which means it's going that way, and that way, and that way, and that way. And that's how you do one with a side-on bit. If you had any questions from today's video, leave something in the comments below. If you wanted me to make a follow-up one with more questions like this, leave something in the comments. But otherwise, I'll see you guys in the next video.